Hi everyone, I hope that you remember me from last year. My name is Juan Carlos Cuestas. As I announced, I am going to go through some of the slides that we covered last year. As I mentioned in my announcement on my email, we are going to build on what we covered last year. And in order to make it a bit easier, I decided to record this video so as to go through the important bits that you need to remember. Okay, you will see that I'm going to skip many things because we don't really need to go through the mathematical derivations. I just want to make sure that you remember some important stuff for this course. Very good. So I'm going to use, as you have here, the same slides that we had last year, exactly the same ones. So if you still have access to them, you can use them. If not, well, you can go through them with me here on the video. Very good. So in this model, in this type of models, we are considering more than one variable. That's what we call the multivariate models. Multivariate models are very useful because they are the cornerstone for estimating structural models, which allow us to understand the relationship between variables. I'm going to skip lecture 1 from last year because lecture 1 is something that we cover because we have to. Is something that give us some intuition on how things work, but actually they cannot be really used very much for understanding the relationship between variables. Those were the univariate models that we are going to skip for now. Very good. So one important thing we have to bear in mind is that when we talk about multivariate models, what we're trying to do is to explain one variable as a function of other variables. Okay, for example, if we say that we want to analyze the evolution of unemployment, then we would say that unemployment depends on GDP growth, on inflation, on interest rates, and so on. Okay, but at the same time, we have to bear in mind that those dependent variables also depend on unemployment. The GDP growth is going to depend on unemployment, is going to depend on interest rates, and so on. So all variables are interrelated. And that in practice, when we try to estimate models, is a bit of an issue. Okay, so let's just recall a couple of things. So if we look at equations 1 and 2, you can guess that what we have there is one equation for demand, one equation for supply, quantities are Q, prices are P. So mathematically we know how to solve this for Q and P. This is two equations, two unknowns, and we can do that very simple. So we are assuming that we know Q and P. But in econometrics, or what we try to do in this modeling, is the other way around. We actually know Q and P, but we don't know the Greek letters. It's alpha, beta, gamma, kappa, etc. We don't know them, and we want to estimate them because we want to understand the relationship between the quantities and prices. Okay, and then it's when we have a problem, and I'll explain you in a second what the problem is. So we can rewrite those equations as equations 4 and 5. We call them equations as a structural, or this is what you have there, simultaneous structural form of the model. And basically we have removed all the subscripts for time. Okay. Again, mathematically, if we know Q and P, this can be solved. Sorry, if we know alpha, beta, gamma, etc., and we don't know Q and P, this is very easy to do mathematically. But in practice, we actually have historical data for Q and P, but we don't know these alpha, beta, gamma, etc., and those are the guys that we want to estimate. Okay. As you have in the third bullet point, I'm going to move myself a little bit here. It says P and Q are endogenous variables and S and T are exogenous. So we are assuming, or we are saying here, that P and Q are the ones which are determined by the other variables. Okay, very good. So this is how we would solve the problem mathematically, if we know the Greek letters but we don't know Q and P. Okay, so I'm not going to go through it because this is not what interests us. What actually interests us is to know how Q and P depend upon each other. Okay, so we want to estimate those Greek letters. So one option that we have is that we just estimate an equation for Q using OLS, as you have on the first bullet point, and then another equation for P using OLS, and that's it. But that is not a very good practice because both equations are correlated, and then problems may arise, as you have there on the second bullet point. The classical linear regression models, the CLRM assumptions, one of them is that there is no correlation between the variables and the error term, and in this case they are correlated. Okay, we'll see in a second where the correlation comes from. So if let's suppose that we don't really listen to this advice and we just go through and we estimate this beta hat that we have there by OLS separately, well then problems come, because as you have there, if we obtain the expected value of this beta hat over here, if I can, yes, here, you would see that it is showing that it's going to be equal to something which is the real beta plus something else. Okay, so now if this something else, if I can get it here, is 0, that means that U, the error term, and X, the variables, are not correlated, then this is 0, this disappears. Okay, and then what we have is that the estimated or the expected value for this beta hat is actually the real one. But if this expected value of X prime U is different from 1, is different from 0, that means that they are correlated, then we are having what we call a biased estimator. Okay, so if that's the case, then we have to do something about it. Okay, all this, why? Because we need to show that if we have correlated equations, the error terms of the equations are correlated, we cannot just simply estimate equations separately by OLS. Okay, this is what the problem that we have mentioned before. Okay, we can just skip. Very good. So how can we do it? Well, this is going to lead us to the useness or the usefulness of VAR models. Okay, all this is to explain why we need to understand and why we need to estimate VAR models. So let's suppose that we just separate P in one equation and Q in the other equation. Okay, so we could equations 10 and 11, they can be estimated separately by OLS because there is apparently no relationship between them. However, we have T on the equation 10 and we have T on equation 11, and what we are interested to estimate is not those pi 0, 1, 0, pi 1, 1, pi 2, 1, 2 in the equations, but the original ones. Okay, we have transformed the original problem into two equations in a way that we have one equation for P and one equation for Q, and from there, from those estimates, we want to go back to this alpha, beta, gamma, etc. Very good. Where is the real problem? So if we have a supply and demand equation and we want to estimate this alpha, lambda, beta, and mu that we have on equations 12 and 13, is that, okay, we can write equation 12 and 13, but which one is the supply and which one is the demand? We know from the economic theory that the sign of beta and mu is the one which is going to tell us whether we have a supply or a demand equation. But like that, we cannot say if the first one is going to be negative and the second one is going to be positive or otherwise. or the other way around. So that's what we call a not identified or under-identified problem. Okay, very good. Blah 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 blah. Okay, just I'm not going to stop too much here. So let's stop for a second. What we are saying is that when we have more than one variable and we want to estimate the relationship between these two variables, we have to bear in mind that there are other economic variables involved which are related to each other. Now the problem is that when we want to write mathematically the equations of those relationships, we encounter that the error term, the shocks are correlated, the variables are somehow connected. Okay, so what we try to do, what we are going to do now with the VAR models, is try to separate them in a way that we can estimate the models without creating too much problem or too many violations of the classical linear regression models. Okay, that's basically what we are going to do. Here we explain a bit more with detail this simultaneous bias problem. I'm going to skip it. Test for exogeneity, I'm going to skip it as well because this is all not necessary. And well, this recursive system could be quite interesting. This is basically to show you that actually there are ways, and this is how we are going to walk to the VARs. Okay, there are ways to estimate multivariate models avoiding the problem of simultaneity. For example, we have there equations 21 to 23. In equation 21, what we have is that y1 is equal to beta 10 plus x1 plus x2 plus some error that we call u1. Okay, very good. In equation number 22, we have that y2 is equal to beta 20 plus beta 21 y1 plus gamma 21 x1 plus gamma 22 x2 plus u2. In the last one we incorporate them all, so y3 basically depends on y1, y2, x1 and x2. So what we have is that equation 1, as you have this written there, contains no endogenous variables, because in the first equation, as we have here, what we have is that y1 does not depend on any of these other y's, right? So that one can be estimated by OLS. It's not a problem. The second one, equation 22, it says contains endogenous y1 together with exogenous x1 and x2. So we can use OLS on 22 if all the right hand side variables in 22 are uncorrelated with that equation error term. So if y1, x1 and x2 are not correlated with u2, which is the error term. So, but what is the problem? The problem is that we have y1, but is y1 correlated with any of the other variables? Well, as you have there, it is not. y1 is not correlated with any of the other variables. In fact, as you have there, in fact, y1 is not correlated with u2 because there is no y2 term equation in the first one, in 2.1. So y1 does not depend on y2, and because it does not depend on y2, it's not going to be correlated to u2, the error term. Remember, the problem of correlation has to do with the fact that any of the variables are correlated with the error term. Okay, so we could also estimate the second equation with OLS, and for the same principle the third one as well. Okay, because in y3 we have y1 and y2, but in y2 we don't have y3, and in y1 we don't have y3. So if you go back, equation 21 does not contain y3, and equation 22 it does not contain y2 either. Okay, so in this type of setup, you see it's a recursive system, we would not have any problem with estimating the equations separately. That's the principle we want to follow when we construct a VAR. Okay, I'm going to skip this. I'm going to skip this because these are ways to solve the problem, but I'm not interested in these ways to solve the problem because I want to go to the VAR models. Okay, instrumental variables, very nice. Okay, the VAR's vector autoregressive model. What is this? Well, the idea is that we estimate one equation. Let's suppose that we have two variables, y1 and y2. So we are going to estimate, or we are going to write, before we estimate, an equation for y1, so as it depends on the past values of the same variable of y1, okay, but it also depends on the past values of y2. That's why you have there also that it depends on y2t minus 1, y2t minus k, okay, and k is the lag or the order of lags. The same story for y2. We write it in a way that y2 depends on, let me see if I can point this. I struggle with this mirroring camera. So basically y2 depends on the past values of y2, but also, if we keep going, on the past values of the previous one. And my finger has disappeared. Very good. This is a VAR, and both equations could be estimated separately by OLS because these equations, as they are written, there is no contemporaneous effect of one variable on the other. Okay, so this could be easily estimated. Now, the problem that we have with this type of models is that they are very difficult to interpret as they are, because what is the meaning of one variable depending on the past values of the other variable? How can we give interpretation to that? Okay, this is basically how you can compact it, but basically this is what we are saying is that we have this one is a matrix, okay, a matrix of all the endogenous variables, and what we have as well is a matrix of the lags t minus 1 of those endogenous variables. In a VAR, all the variables are endogenous, okay, by principle. Very good. Don't worry about this. And about the Beckhems we'll talk about it later. Okay, so the good thing of a VAR is that it's easily estimated. Okay, the problems with the VAR is that they can be very big if you start including all the lags and all the variables that you have there. They are theoretical, they are very difficult to interpret as they come out of the oven, basically. And we have also the problem of stationarity. We are assuming so far that all these models are stationary, so there is no problem, but we may encounter issues with that as well. But the main problem is that the last one, is how do we interpret the coefficients that we obtain directly from the oven. Okay. One extra problem that we face here is the lag length. We have written before that it could go to t minus k. So what is k? K is how many periods in the past we are including in our model. How do we choose it? Well, to you, I would say don't get too worried about that. We have other problems to worry about. Life is complicated by itself. I would just use one of these animals here. Is what we call information criteria, and EDUs or any computer does it automatically. You can just choose the lag length depending on these information criteria. So you should not worry too much about this right now. In practice, then things get a bit hectic, but for now we can just leave it as it is. Okay, now it says there, does the VAR include contemporaneous terms? No, it doesn't, but if it does, then we have to do something about it. It's what we call a structural VAR. And the problem with the structural VAR is that, again, they are normally under-identified, so they are not properly identified, and we need to give some impose some restrictions so as to identify. Okay, why we need to identify the model? Because from this VAR model that we have here, okay, what we want to do is to go back to the structural model, a structural model where we have contemporaneous values of the variables both on the left and on the right, okay, because that is more meaningful. Okay, so let's look at this. So basically this comes, let me go back. Okay, yes, so we are going to include here contemporaneous values of the variables. So you can see in the first equation, the last, let me see if I can make this thingy work. Can you see? Yes, you can see something here. So, no, you cannot see. Okay, so at the end of this equation we have that we have alpha 1, 2, y2t. Well, y2t is contemporaneous. Okay, so we are including contemporaneous values of the other variable. The same in the second equation. In y2t, in this equation, we are also including contemporaneous values of y1t. So what we do here is that we write it in matrix form because it's easy to see, but don't worry too much, so as to show that at the end, and my finger is going to disappear, very good, at the end basically what we have is that we have a matrix of coefficients, which is alpha 1, 2 and alpha 2, 2 with the zeros in the corners, multiplied by another matrix which is y2t and y1t. We cannot estimate this equation separately because they have contemporaneous variables. Now what we do here is that we are going to move everything which is contemporaneous to the left hand side of the model and everything which is lags to the right hand side of the model. That's why we have this. Okay, so what we have done is to move to the left everything which is contemporaneous, and we have left on the right everything which has lags. Okay, so then we are going to call B this matrix with coefficients, this one here, and if we actually move this B to the other side of the equation, this basically we are somehow saying that we have rewritten the model in a VAR way so as not to have contemporaneous values of the variables on both equations on the right hand side. Okay, so this, if we just, instead of beta or b minus 1 times beta 0, we compact it in something else that we will call a0, then with the VAR we can estimate this a0 and a1 very easily, and then go back to the original ones, which is these ones here. Okay, very good. I normally say in class, do you have any questions, but I guess that is not, it's pointless. Right, so let's don't worry too much about this block significance and causality test because I'm not really interested on this right now. Okay, here is where we go. So what we have to do is we want to estimate a structural model. We cannot do it directly, we have to estimate a VAR. And from the VAR we want to be able to say something about the structural relationship of the variables. Structural in the sense that what is the effect of the contemporaneous shock of one variable on the contemporaneous values of the other variable. Okay, so what we do is we estimate a VAR and we play with this thing of impulse responses. Okay, because with impulse responses, this is basically a graph where we can see how the variables move when we give a shock to any of the variables of the model, and that's very useful because then we can understand what is the relationship and give an interpretation to the VAR. Another thing that we can do is to use this, or to estimate this variance decomposition, which is also quite useful. And this variance decomposition, what it's telling us is how much of the variance of our variables depend on its own shocks versus the shocks on other variables. Okay, so they are both quite useful. We are going to focus though on the impulse response functions. The ordering is relevant because we'll see in a minute that the impulse response functions that we want to estimate are structural, in a sense that we want to see what is the effect of a shock in y2t on the current values of y1, so on y1t. Okay, so we again estimate the VAR, and from the VAR we try to go back to the structural model. Okay, so basically this is what I showed you before. Okay, the idea is to again estimate this model that we have here and go back to this one, but it's not that easy. And it's not that easy because what we know is that we can estimate this one. These are the guys we are going to get from eViews or R or whichever computer program that you use. These are estimates. How the hell we go back to the B's, to the betas, okay? Okay, remember that what we have here at the end of the equation is E1t, E2t's. These are not the structural shocks, or they are not the shocks from the structural model, which the structural model is the one which contains contemporaneous values both on the right and on the left, and we have explained many times that that cannot be estimated directly, or not normally. So these guys here are related to these shocks of the structural equations, and how they are related with these equations that we have here. Okay, so this first one, if we could rewrite it, or if we could, well, we can go back for a second. You see, on this equation at the end, on those equations at the end, what we have is epsilon of yt and epsilon of zt. Okay, those are the shocks of the structural models. Those epsilons are not observable. These ones are observable. These e's are observables, and we want to know how we could relate these guys to these epsilons. Okay, so there's a equation here, there's a way to do it, but that implies knowing those b's, b1, b2, b22, and so on, and those are the ones that we don't know, because those are the ones that we want to find out. Okay, so the important thing that we need to have, or the important stuff that we need from a VAR, is what we call the variance covariance matrix, which is this guy here, and it's how those shocks are related, and that comes from this one. Okay, okay, so we estimate our model. This is basically VAR comes from AR. Remember, on the first class of last year we talked about the autoregressive models and the moving average models. The autoregressive models basically relate the variable with the past values of the same variable, right? So, and we also said that from the AR model we could inverse it, or we can obtain the moving average model, AMA, right? And basically this MA is what we are going to call the impulse response function. C that we have here is YT depends on the previous values of the shocks, and that's an MA model that we covered last year. Okay, very good. So let's suppose that we estimate a VAR of two equations. We have here, sorry, I would like to be able to be better with this mirroring. So we have two models, one for x, one for y. This is VAR because you see here we are only including the lags of both variables. Okay, we don't have contemporaneous variables on the right hand side. So this is an estimation of VAR. Okay, so we obtain the parameters 0.7, 0.2, and then we have the error terms. Okay, so what we can do is we can see if we give a 1 unit shock to the first one, okay, the shock goes in the error term. So this 1 would go on the E of the first equation. Here we will put 1. And then if we put 1 here, of course this 1 is going to give us a 1 here. That's why if we give a shock of 1 in this error term, the first value for xt is also 1. Okay, and how this 1 affects yt? Okay, so we have this relationship here, which is telling me that the error terms are related in this way. Okay, so if I have 1 here, the shock in the second variable is going to be 0.1. times 1, which is 0.2 times 1. So a shock on the first value of the variable is going to affect the second one by 0.2. Okay, very good. So we have the contemporaneous effect. So a 1 unit shock on the first one affects 0.2 the second one. But because we are making an assumption here, and these are the assumptions that I keep talking about, or the restrictions I keep talking about. Okay, very good. And now it would be very easy, because with an Excel spreadsheet, because you could just obtain what is going to be the effect of the first one. So this is going to be on the first period, 0.2. You put it here, and you have here 1. That number here is going to be 0.74, and so on. Okay. Well, this is one impulse response function, and we can plot it, and we'll see it in a minute. But we can do it the other way around. We can say, okay, we give a shock of, sorry, my finger doesn't reach, but we can go to the other side. Okay, maybe I can move myself. It's not going to be very good, but I come here. Okay, so let me see if I can do something here like this. Yeah, you can see my finger. Very good. So we can just give the shock to the first one. Instead of giving the shock of 1 to xt, we give it to yt, we give 1. Because the relationship between the error terms go from E1 to E2, as we have in that equation for the E2, and not the other way around, this 1 unit shock on yt has a zero effect on the previous one. Okay, and again, this is why we are making assumptions. So we are making the assumption that this oh, sorry, we are making the assumption that oopsies, we are making the assumption that these guys are related in this way. So E2 depends on E1, but E1 does not depend on E2. That's why here, yes, there is a contemporaneous effect between them, but on the other one there is no contemporaneous effect. Okay, and this is by assumption. We could have made the assumption the other way around, but that could be a different story. Okay, so depending on which assumptions you make about how correlated they are the error terms, and that's something that we have to kind of guess or look at the economic theory, then we are going to have different effects between the variables. And that's one of the criticisms of these VAR models, no? That you have to make a lot of guesses. Okay, so this would be the representations of these two impulse response functions. Okay, very good. Of course, if we could know this B1, B2 and so on, we could easily go back to the structural model, but we don't know those guys here. So as we have there, the problem is that what we observe is E1 and E2, but not these epsilons, which are the ones which come from the original models. Identification, well, one way is what I have shown you is recursive modeling. So you first put one variable and then you put the other one and assume that the relationship goes from one to the other on the contemporaneous time, but not the other way around, otherwise it cannot be identified. Okay, how do you choose which one goes first? That's the problem. Normally we have to use some model for this type of identification. Very good. This is how, you know, mathematically it would look like. And here we also talked about some examples last year. Right, I'm not going to go deeper on this. I think that you have a grasp of what this little class of, I think that last year we did it in 3 hours and something, 4 hours. And now we have done it in less than 40 minutes. So I hope it's useful. Thank you very much. I'll see you soon.